All right, there's one point of contact.
Is it the same thing with the sled in the ground? Start going up on the sled and going down on the ground.
And a different subscript. All right.
Going up for the dad and going down on the ground again.
And any other objects touching?
The rope in their hand, but I don't know.
That's why it's being lumped into tension. Is it wrapped around the man's hands, or is he just sort of holding it? So, I don't know. So yeah, and rope and sled, same thing, we'll call them in tension. That's it. So, normal force done. And now friction. Let's do the easy one. I've got 3 pairs of normal forces, so potentially I have 3 frictions, and in reality I do have 3 frictions here. Easy one, sled and ground. Which way is friction acting on the sled? You seem hesitant, Becca. Don't be hesitant. Say it with conviction.
To the left.
And I saw a couple of people, other people gesturing the same way. Because the sled is moving to the right and friction wants to oppose that. And now, the other two probably equal complexity. Let's do boy and sled. Which way is friction acting on the boy?
To the right.
Why?
Because it's the opposite.
It's the opposite of the left, I'll agree with that.
I don't know. I'm having a hard time putting it into words. But I mean, I've like seen or saw it. I can't put it in English.
Someone want to help them put it in English? Or contradict them and put that in English? Besides, you're wrong. How could you?
Is it could be over left because the sled's going to the right?
Well, at this point, you've given both answers, left and right, so one of those is correct. All right. Sled. The boy. Was that hand raising or your?
Okay, so if the sled is going this way, right?
Okay.
So wouldn't that be, making him want to go back this way, the board? So
Yeah.
Wouldn't that be the opposing, arrows or whatever, or?
Because it's the desired relative motion. Relative to what he's touching. If the sled were frictionless, that boy would go this way.
Right.
So therefore, friction opposes that, friction's acting this way. You were correct the first time.
That's exactly what I was seeing, but I was just having a hard time Englishing it.
The other bit here is the fact that I said the acceleration was to the right. Now I am assuming that the boy is sitting on the sled and he's staying on the sled. That the dad's not ripping the sled out from underneath him. Even that is the case, he still would move forward just a little bit. If he's accelerating to the right, then there must be some force to the right. There's a very strong link, which we officially get to in chapter 4, very strong link between force and acceleration. So there has to be some force acting to the right on him. So another justification. F sub D, and then F sub D. I do want to point out when I talk about no man's land, this F sub B is not technically written on the sled. I'm running out of room there, but I think it's very clear. If I'm looking at that and when I'm grading, I'm going, yeah, they clearly mean that to be on the sled. All right, and now dad and ground.
You got this one foot on the ground, correct?
Right? He's sort of,
Yeah.
Would it be going left for the dad?
why?
Cause he's trying to go that way.
He's going
Well, the action is right.
Right, acceleration.
Accelerate, yeah.
So the dad is going to the right.
He wants to get pulled.
his desired relative, is right?
Relative to, what's the relative piece here?
Is it the ground?
And,
Sled?
no, we're talking about dad and ground. All right, let's take a look at it from a slightly different point of view. I'll assume this is stable enough. We did have a table collapse a number of years ago. All right, so dad, the back foot's on the ground. Think about, right now, there's friction between my foot and the paper. When I step forward, which way does the paper go? So, what we're talking about here is not, the dad is going to the right. But more importantly, his foot is actually going to the left. When you walk, you push backwards. You're pushing your foot opposite the direction you want to go. And so because the foot it wants to go to the left, the friction opposes that. Another way of looking at it is the dad is accelerating to the right. That was saved in the problem over here. The acceleration is to the right. So there's got to be some force acting to the right, especially since tension's pulling them back. There's got to be something acting this way. Now, some students mistakenly look at that and they go, well, I know there's some force to the right, so let me just add an other in here. This mysterious force, hand of God, Jedi something. And they'll label it F sub push. Or there's no mysterious force. It's the foot wanting to move to the left that causes the dad to move to the right. And that is the force diagram. We will be coming back to force diagrams throughout the course. It's one of the reasons why we spent an entire class on it, or 2 hours on it. But being able to understand the forces involved becomes really helpful as we get into more and more complex physics. All right, questions to hear? And I will guarantee you, there will be a problem of this caliber. It won't be this one, of this caliber on the test. All right, why don't we take a 5-minute break here, come back, and again, I'm just gonna let it roll because I'm more apt to forget to turn it off. But to check power though. And when we get back, we'll finish up chapter 2 and talk about the quiz. So a couple of miscellaneous topics from chapter 2 to wrap it up. The equilibrium problem, or the equilibrium problem. So if we have a person standing on some sort of scaffold that is being held up by 2 wires. $30-kilogram scaffold or beam, we have a 70-kilogram person standing on it, and the tension in this wire is 1,200 newtons. What is the tension in that wire? So if we think about the forces here, I've got beam, I have person, and I'm going to go ahead and consider these 2 wires to be categorized as other. I'm not telling you how they're connected up above. They're connected to something up above. And I am assuming that there's ground far below. I guess. Yeah, so other are the two things that have given you in the problem. So this is 1,200 newtons, and this is some tension. Technically, I should have a separate subscript. So why don't we T sub L and T sub R for left and right. All right, so what are the forces involved? I got other already taken care of. Anything else?
Yeah, what?
Other.
Okay.
Contact.
Therefore, which force?
Normal.
Yeah, normal. The contact force is a normal force. The normal force between whatever that is. Let's just say beam.
Yeah, beam.
All right, so I have this, the beam is holding the man up, and the man's pushing down on the beam. And what else?
Which letter is the check for? O?
That's what, I didn't really, you could call this tension, and I labeled it as tension right there, or I labeled it also as other just because I didn't talk about what was holding it up. Where's the other end, these ropes or whatever this is holding this thing up?
Which one's the check mark?
Oh,
It's the
oh.
standard.
That's, or it could be actually, I'm lumping them together.
Okay, my bad.
The intent was O, but as I talked myself into, I could just merge them. Normal force, that's the only contact that we have in the problem, other than whatever the ropes are attached to up there, which we don't care about. What about friction? Nathan's saying no. Erica?
I just had a question. I thought you said we didn't need subscripts for tension for the FT and U.
Well, because there are 2 different ropes.
Oh, okay.
If it's all part of one rope, if I have this somehow connected magically and it comes back around, then I could label them the same. But then the problem becomes very different. What are we missing?
Is it weight?
Yes, what was it? I heard something over here.
I was about to say, well, you said something about friction, but he's not moving.
All right, right, he's not moving, but is there a desire to move?
There it is.
Down? Would it be down? I mean,
Friction is parallel to the surfaces of contact. So we have person standing on beam. If the surfaces are up vertical so that the friction will be down, this guy's in serious trouble.
So he's walking?
I thought we were still doing the normal. I'm sorry. That's why I
I
said.
did start off with friction and then I suddenly shifted over to weight, so I apologize for that. So why don't I stick with, let's just do friction right now, then we'll talk about weight. All right, so friction. Is there desired? Does it look like I've drawn this to be level?
Yes.
Yes.
Okay, the guy's just standing there, so there's no desire for him to slide one way or the other. I'm not putting a tilt into it. So friction, there is no friction in this problem. Now, if you want to put his life into danger and suddenly tilt that thing, go for it, but that's not what we're doing right now. All right, weight. Weight acting on what?
Beam.
Okay. So I have weight up beam. Weight up beam. And
On the man on the beam?
Man and ground.
man and ground.
Oh.
If you had a significant force between you and something you're touching, then I suspect you would never actually be able to get up off that chair. The force between you and the object that you're touching, unless it's the ground, is small. Even the ground though, technically, the distance between you and the earth is gonna be roughly the radius of the earth. We'll get to that more in chapter 9. All right, so weight of person, and then weight of person. As I stated at the top, and I didn't actually write it down, this is an equilibrium problem, so let's just make that abundantly clear. Equilibrium. So the total force is 0. The force is up equal to force is down. So let's start out with the man. First off, let's figure out what his weight is. There's a formula for weight. W equals mg.